coding. So, okay, let's continue, and we're talking about our old friend Green. There we go. We're dealing with our old friend Kirchhoff. And so this is a system of keeping track. The problem you have with some circuits is that there's more than one power supply. I know that seems weird, but there is. And the power supply in some lines are adding together, in other lines they're fighting each other. So different parts of the circuit have different effects, and it's hard to keep track of these things. So Kirchhoff came along and developed a way of codifying the signs, basically. It's not that people can't read the EMF on a power supply, they can. And it's not that they don't know that the potential difference across a component equals, I times R through the component. They do. It's that they don't know what sign to give these components. They don't know what sign to give the equation. And so Kirchhoff's rule is a methodology for sorting that out. It's not the only one. Later on you'll do things like Thevenin's theorem and stuff like that, which are different ways of approaching, more mathematical for more complicated circuits. But this is that next level of analysis. And we use it in the next sections, which is probably why they introduce it. So circuits consist of, if you think about it, if I draw a simple circuit, there might be a power supply, there might be a resistor, there might be a resistor, there could be a power supply, there could be a resistor. There's just 3 resistors but 2 power supplies. And what we recognize is there's a junction here and a junction there. And so the current flowing around this bit here is constant in that part. And the current flowing around this bit is constant in that part. And the current flowing down that bit is constant in that part. So what we learn to do is at a junction, not both of them. If you define it at one, you define it at the other. So you pick a junction and you just name currents. So I'm going to call this I1, this I2, and this I3. Now, can you see how my previous naming system is falling apart? Because before, I1 was the current through the 1 ohm resistor, and I2 was the current through the 2 ohm resistor, and I3 was the current through the 3 ohm resistor. And that's no longer convenient, because we have, it's just no longer convenient. You got a question or a comment?
Yeah, why don't we just do IA, IB, IC?
So if you want, do IA, IB, IC, but I've always done it this way, so I'm going to, yeah. So, you pick. People are sometimes uncomfortable about picking. What if I pick the wrong direction? All that will happen is, if you find I1 and you happen to pick the wrong direction for the arrow, you'll get a negative sign on your value. Saying, oh, you just picked the wrong direction. It's no big deal. So do not try to finesse it. Do not try and work out what should I put down. My suggestion is you just pick a certain geometry and always put down the same geometry. So for a junction, if I look at my logic, I have I1, that's coming into the junction, and so is I2. So I2 is coming into the junction, and that equals I3, because that's leaving the junction. Yeah? Current is not created or destroyed at the junction, so what comes in must equal what goes out. Agreed? That's just logic. So that's the first little bit of logic behind this. And then there's a second little bit of logic, which is basically, I'm going to do this in green, is basically how I sort out my voltages, be they EMFs or potential differences. And for that, I have to invent a way of visualizing. And so I have what I call a loop. Because logically, the EMF inside a loop must balance the potential difference inside the loop. What I make, I spend. So I need a way of getting the signs right. And so what I say is, for an EMF around a battery, if my loop, this is just, it's not the current, it's a visualization. If my loop leaves, imagine it going through the wire, it enters the battery, and it leaves the battery, because of the way I draw it. If it leaves the battery via the positive terminal, it's a positive EMF. So this will be a positive EMF. Because it's leaving via that positive plate. Can you tell me for this other one over here, what kind of EMF will that be? Well, if you look, it's entering through the negative plate and it's leaving through the positive plate again. So that's still a positive EMF. So it's not to do with clockwise, counterclockwise, or, it's just to do with where that thing, it is to do with clockwise, counterclockwise, but it's how that plays out with the position of the power source. And then what about these IRs? We know the voltage drop across here is IR. But is it positive IR or negative IR? And what we say is that if the current flow direction is the same as the loop direction, it's negative potential difference. So for this one, this is a negative potential difference, and so on. Okay? We'll do examples. If it's the same direction, if the current is going in the same direction as the loop, it's a negative potential difference. Yes?
How do we figure out which direction the loop is?
You draw it.
Oh, you just draw it.
You draw it and put an arrow on it. Yeah, you pick. So I do these things very standardly. I tend to draw the same current pattern, I think. I don't ever try and change it. And I tend to do clockwise loops. Yes?
So it's just arbitrary that you have the two current loops going in different directions?
They're going in the same direction. They're both going clockwise.
So what's the red line?
They're the currents. And that's because I picked I1 coming in and I2 coming in. So the current flowing on that arm of the circuit must be flowing in that direction because I defined that there. And because I defined that there, that means the current must go in that direction. Yep. And you pick that. As long as what you draw matches that equation, you're golden. So this is a little bit uncomfortable in that you've got to pick current directions and loop directions. And people don't like that, but you get used to it. But it's strict in that you've got to live with what you draw. And when I'm grading this, I look at your diagram. And if the current directions and the loop directions are clearly marked, then fine. I continue. If your equations match your diagram, you get points for that. And then if you do the math at the end, you get points for that. If you get the right equations and the wrong math, you lose a little bit. Wrong equations and it's more. I don't care if you can do the math on something that's wrong. So the key thing is to get the right equations and then go from there. Let's do some. So just so you know, there's a junction rule. Let's just read through these. So the junction rule says the sum of the currents entering a junction in a circuit must equal the sum of the currents leaving the junction. That makes sense. Then the loop rule is the sum of the EMFs and potential differences, they're the voltages. The sum of the voltages across all elements, power supplies and resistors of a closed current loop must be 0. So, okay. And then the sign convention I've got written down there. Sign convention, sign convention. Let's do one. I need to move this little guy out of the way. So again, people are kind of uncomfortable, so I just pick a junction. I tend to pick the top one. Did I get rid of my pen? I tend to pick the top one. And I'm just going to call this I1, I2, and I3. And then I do my loops like that. And I'm set up. So I go junction, rule. And I got to tell you, you know, as I grade more and more pieces of work, I'm really grateful for people who actually tell me what they're doing. It tells you what you're doing, and it also tells me what you're doing, and I can follow what people are doing when they put stuff like that down. So I'm more inclined to stick with them if the answer's not right. But if it's just numbers on a page, I get to the stage where it's like, I got to grade these things, and so I'm out of there, you know. So I'm not saying I'm going to punish you because you're not tidy, but the more information you can give to me, the better. So a junction rule, and the junction rule says that I1 plus I2 equals I3. How many unknowns do we have? I've been asked for the current through the 5 ohm resistor, but how many unknowns do I have in my system? Do I know the EMFs? Do I know the resistors? Do I know the currents? So how many unknowns do I have? Now look at your diagram. How many unknowns do I have? How many? It's 3, isn't it? So let me finish. So then how many equations do I need? 3 equations. Now you have a question?
Yes, can you have a junction both directions?
Oh, you can.
1, 2, 3.
Yeah, so then you'd need 4 equations. Yeah, you can. This is just, you know, and this is again that trade-off I make where I could throw anything at you and you could solve it, but it would take you longer and you're more inclined to make mistakes. And you might look at that and say, I'm not even going to try that. And I don't want the test only to be about 3 questions. I could pick 3 things and say, if you can do these things, you get an A, and if you can't do these things, you fail. But that's not what I'm trying to teach. I'm trying to teach a little bit of everything, yeah? So then the problem is I got 12 things, and so the hard things, you might be inclined to say, forget that. You know, I'm not even going to bother with that hard thing. So the trade-off is that I will pretty much give you a circuit that looks like this. I'll move the resistors around. I'll switch the power supplies backwards and forwards. But you're not going to get 4 things in there, and, you know, it's going to be a 3 unknown problem. And if you know how to do that, my idea is then, in principle, you could do the 4 unknown problem. So, question and comment in the back?
Could you explain again how you got your loops?
I decided. This is all about me. There's no logic behind it apart from the fact I need to draw a loop. There's no physics behind it. It's just you draw a loop. It's a point of interest, and it's a way of keeping track. Having drawn it, I live with it. It's like if you remember back to physics 1 and you had this axis and you said, I'm resolving forces on this axis, and you said that's the positive end and that's the negative end. And sometimes it wasn't obvious which was the positive and which was the negative. And you picked, you just said that's the positive end and that's the negative end because you've got to keep track. Same thing with this. It's just, you've got to just put the loop in and keep track. It's bookkeeping. So then let's do a junction, let's do a loop rule. So loop. So now let's look at our left-hand loop, and I'm going to start off. Doesn't matter where you start, you're going to do all 3 of them. This is leaving via the positive. I know that because it's the long line. So the loop is going through the power supply and leaving via the positive. So that's just not 6 volts, that's plus 6 volts. And I'm going to add to that because it's a sum. I've got to add all these voltages together. Now this is 3 volts and I1's going through it, so it's going to be 3I1. That's the magnitude of it. But I look and say, oh look, my current is flowing from left to right and my loop is going from left to right, so that's negative. And then I do my third, which is, the other loop. So, this same loop. So then I go, it's going to be a 7 I3. And I say, well, my current is going downwards, and so is my loop, so that's a negative I3. Everybody see where that comes from? I'd like you to do the appropriate equation for the next loop. Can you do that for me, please? Yes.
So why is it positive 6?
Because this loop, can you see this green loop?
Yeah.
The loop is following the line, and it enters the battery through this plate. And that plate is a short line, and that symbolizes the negative terminal. And the long line, I mean, if you think about it, it takes twice as much ink to draw a positive as it does a negative.
Yeah.
So they do a twice as long a line. Yeah, cool. Yep.
Yeah, I don't follow the whole I1, I3 thing.
Yeah.
So you pick.
Yeah.
You know current's
I mean,
flowing.
The loop rule, you got the plus 6 and then
Oh,
the
I'm
minus 3 I1. I'm really
Yeah,
lost.
that's very
So,
No, I understand, like,
So-
it's...
so just listen here, and I'll go through it again, okay? So I have I1. Is I1 going to the left or to the right? Look at your diagram. Is I1 flowing to the left or flowing to the right? What is it? Pardon?
To the right.
To the right. And now imagine your loop. I draw it in the middle of the gap, but that's just so you can see it. Imagine the loop is traveling along this wire,
Yes.
and it comes to that component. Is it traveling through that component to the left or to the right?
To the right.
Look at the direction of the arrow. Imagine it goes along. So it's going to the right. Agreed? And the only thing, it's completely made up. It's arbitrary. There's no physics behind it.
Right.
Is if they're in the same direction, it's a negative. Okay? That's just bookkeeping. It's just because...
So are you saying that negative 3 times I1 is equal to the voltage? Is that what that's saying?
I'm saying that the potential difference across here is IR, which is I1 times 3.
Okay.
And I'm saying its sign is negative. Yeah. Cool. So, okay, let's do this other one. So, I look at my loop, and I'm leaving the EMF source via the negative. So that's just not 9, it's minus 9. It doesn't matter which order you do these in. I'm not fussed about the 7 I3. I'll do that next. It doesn't matter. I'm going to add on to that, and I look at this, and I'm looking at the 7 ohm resistor, and I see that it's going to be, first of all, it's going to be 7 I3. That's the magnitude of it because it's IR. And I see that the current is flowing downwards, but that the loop is going upwards, and that's a positive. And then I look along here and I say, oh, well, look at this then. I have a 5I2, and the current is flowing to the left, and the loop is going to the right. That's going to be a positive I2. Okay. Yes.
It's also the same question. Why is it negative 9? I thought it was supposed to be plus 9.
So, imagine this little point, this green point. I drew it in the middle of the thing, but imagine it's going through the wire.
Okay.
So your finger goes up to the junction, and then it goes off to that corner, and then it comes down. And you're entering through the long line,
Oh.
and that's a positive terminal, but you're leaving through the short line.
So we always write the leaving. Not
It's
the
what you're leaving, yeah. It's always what you're leaving. So here I left via the positive, and here I'm leaving via the negative. Yeah. Cool. The rest is math. Now, different people have different ways of solving it. I'll show you the way I solve it, but you can find your own way. And, it's kind of like, hopefully, it'll work. But the way I do it is I turn around and say, oh, look, I have 3 equations and 3 unknowns, so it's solvable. Okay. Could just put down solvable and leave, but, need a number for it. So what I do is I turn around and say, well, I could replace I1 here with an I3, and I could replace an I2 here with an I3. I'd have an equation which was only an I3. So that's what I'm going to do. So I'm going to say, okay, I want to get the I1 here. So I go, okay, going to be careful. I'm going to take this to the other side. So plus 3i3 is equal to 6 minus 7i3. That can't be right. Plus 3i1 is equal to 6 minus 7i3. Everybody agreed on that?
Yeah, that's it.
Take that to the other side, leave the rest alone, and then rearrange. So I1 is equal to 6 over 3 minus 7 over 3 I3. And I strongly advise you to do it in 2 steps, because I can't tell you how many times people do that in their heads and get a mathematical error and just lose points for it. And then we go, okay, now I want to get I2 by itself, leave it alone, plus 5I2 is equal to, okay, take the 9 to the other side, so that's 9. Take the 7I3 to the other side, 7I3. So that gives me that I2 is equal to 9 over 5 minus 7 over 5 I3. Agreed? Then I take these guys and substitute in up here. So I'm going to say 6 over 3 plus, sorry, whoa. Let's erase that. I feel so bad about it, I'm actually going to erase it. Minus 7 over 3 I3. That's my I1 done. Plus 9 over 5 minus 7 over 5 I3 is equal to I3. Six over 3 minus 7 over 3. Let's not do it that. Let's do it a little bit more advanced. Let's take all my terms together. So I'm going to say minus 7 over 3 I3 minus 7 over 5 I3. Bring this I3 across. Minus I3 is equal to, take these to the other side, minus 6 over 3 minus 9 over 5. I've got minus signs everywhere. I've also got 3's and 5's in the, what is it called on the bottom, denominator. So common base 15. So I'm going to say minus top and bottom by 5, 35 over 15 I3, minus top and bottom by 3, 21 over 15 I3, minus 15 top and bottom. Same thing here, 5's tops and bottoms, minus 30 over 15, minus 3's tops and bottoms, 3 9's are 27 over 15. 35 and 21 makes 56, and 15 makes 71, is that right? 71 over 15 I3 minus is equal to 57 over 15. My 15s cancel, my negatives cancel, so I3 is equal to 57 over 71, which equals whatever that equals. I brought my calculator because I bring my calculator. Yes?
Can you set it up to use a Kramer's rule to solve the...
Got to remember what Kramer's rule is.
It's like when you have three separate multiple equations, you can set up a determinant.
Oh yeah, that's brilliant. Yeah, that's brilliant. If you've done that, that's great. And you just write down Kramer's rule and do it. Yeah, brilliant. Yeah. Use the math, but you don't need to know that to it's not a prerequisite. But yeah, I'm happy with that. You got to give me the 3 equations though.
Yeah.
Yeah, I want to know you know the Kirchhoff's rules. That's part of the skill. So then we're going to go 57 divided by 71 equals, so 0.8, am I right? And what can you tell me about the direction of my arrow, I3?
Correct.
It was correct. And now, the only thing I've got to tell you is that's not the final answer, because that is the current through the 7, isn't it? I3 is the current through the 7. So I've got to do one little bit more work. So I've got to find I2. So I go up here to this expression with I2. So I2 is equal to 9 over 5 minus 7 over 5 times 0.8. And I can figure that out. So that's going to be, let's do it backwards. 0.8 times 7 equals, divided by 5 equals, and then bracket 9 divided by 5 bracket minus second answer, and I'm getting 0.68. Does that sound right? And again, a positive value. So I have the right direction for that. Pure luck. I didn't even look at my circuit. It's just pure luck. No, and there's no goodie points for doing it. It's just pure luck. So, what do you think? Which is easier, this or simple circuits? I tell you, more people get this right. As a proportion of the class, there's a higher success rate on this question than there is on the simple circuits question. Yes. Oh no, listen up. I can't hear. I can't hear. People are talking. Yes, please.
The little arrows up top, could you tell the direction of the current from the beginning?
I decide.
So you decide the loop direction and the direction.
I decide all of that.
But once you keep your,
But once I do it, I stick with it. Yeah.
but you have to keep your, it has to stay standard, so you have the current coming from the long side, the positive side. You have to do it for everywhere on that circuit.
It's completely arbitrary. I could reverse all those arrows. I could reverse one of them. My equations would. I could change one of those arrows. I'd change all 3 equations. I could have I2 plus I3 equals I1 just by changing the direction of that arrow. My first equation changes. My second equation changes. Or my first equation changes, and my third equation changes, and it compensates. So there's no physics involved in, there's absolutely no analysis involved in those current directions.
It's just once you keep it standard. Okay,
Just once I do it, I do it. Yeah. And I know that's uncomfortable, but that's the way it is. Yeah. So not bad, eh? Not bad.
Sir, if you change the loop, does that also change the equation?
If I change the loop direction, I change the equation, yes. There is a third loop on this, by the way, which goes completely around the outside. And that's legitimate loop. You can do that. I've just never done it. You get into the habit of doing it, and you just do it. So you could use, there's 3 loops here that you can play with. There's one on the outside of the whole thing.
what is it? 26 minus.
It would be plus 6, and then minus, and then plus for the 5, and then minus 9. Yeah. It works. It works. Okay, so simple circuits, and then Kirchhoff's laws. And yeah, I expect, I mean, maybe I'm going to prove myself wrong, but I would say on my hit list, they're like high on my hit list. Yeah. This next thing is also on my hit list, but it's a different thing, so I want to just clear our minds a little bit. We're going to use Kirchhoff's rules in order to justify a little bit of math. Now, we didn't do Kirchhoff's rules for capacitors, but it's basically a sign convention again, and it basically says, look, if the loop, treat the capacitor like it's a little power supply. Now, You know that if that's the positive terminal of your EMF, then that's the positive plate on your capacitor. And if that's the negative terminal on your EMF, that's the negative plate on your capacitor. So you know those two, they are fixed by physics, yes. You can't just decide that. But you're going to draw a loop, and then you're going to say, what plate do I leave by? It says, if a loop exits the capacitor through the negative terminal, the potential difference across the capacitor is negative. So you're treating the same sign convention as you did for EMFs for the capacitor. You just got to know which is the positive plate, which is the negative plate. Okay, so we can apply Kirchhoff's rules to a circuit like this in the bottom right. This is a resistor, that's, you know, that's the international symbol. So now here's an interesting situation. Everything's clean. There's no charge anywhere apart from in the EMF. And you close the circuit. And the first thing that starts happening is you start getting a positive charge on there and a negative charge on there. And it's pretty easy to add charges because there's not much pushing against you. So you very quickly add the second positive and the second negative, and a bit slower the third positive and the third negative, and now you're beginning to struggle a bit, your fourth positive and your fourth negative, and eventually you get to the stage where the electrostatic force pushing against you, adding another positive charge to the positive plate, is more than the electrostatic force you're getting from the EMF. If you like, the battery doesn't give you enough energy to climb that hill. So you stop. So it takes time to charge up the capacitor. It's not instantaneous. It takes time. So before, when we said, you know, oh yeah, the charge on the capacitor equals the voltage across the capacitor times the capacitance of the capacitor. It was not the EMF necessarily, it was the potential difference across the capacitor. And you can say the charge causes the potential difference, and the potential difference allows the charge. It's like one of these things about chicken and egg. Just because this is 10 volts does not mean to say at all that that 10 volts is all across the capacitor from the instant you close the switch until the end. In fact, that's not true. When there's no charge on that capacitor, there's no potential difference across the capacitor. So now, in simple circuits, we recognize that not every resistor had the EMF across it. Agreed? With a series network, I'm going to come across here. With a series network, we said, well, yeah, you know, not every one of these resistors, if that's 10 volts, this could be 8, and that could be 2, you know, because of the two relative sizes, agreed? But they always added up to 10, and they were always those values. Well, I can tell you that the voltage drop across the capacitor and the voltage drop across the resistor will add up to 10. From the very instant the switch is closed, it'll add up to 10. But it won't always be the same value. So this is a dynamic system. This has got what's called a transient effect. And we've got to do some logic. So let's get the extremes. Let's get what we think will happen at the instant the switch is closed, and then after 5 years. Let's take those two extremes. We'll worry about the actual middle bit a bit later. So at the first instant, when you close the switch, is there any charge on the capacitor? The switch is closed. Now, any charge on that capacitor? No. If there's no charge on the capacitor and the charge on the voltage of the capacitor, remember what we say? The capacitance equals Q over delta V. How much charge you have for a given potential difference. So delta V is equal to Q over C. If I have no charge on my capacitor, then I have no voltage. So in that first instant, I have 0 volts on here, which means there are 10 volts across here, because it's got to be somewhere. Now, the thing that governs the resistor is delta V is equal to IR. Now, the R's fixed, and I know my voltage is 10 volts. So I've got a lot of current flowing through. Yeah. So when the switch is first closed, there's a lot of current because it's easy to charge up the capacitor. That's from a conceptual point of view. When the switch is first closed, there's a lot of current because all the voltage drop is across the resistor, and V equals IR. That's the more analytical point of view. But either way, when you close that switch, no volts across the capacitor because no charge, all the volts across the resistor because the maximum current is flowing. Let's imagine 5 years later. 5 years later, I've still got my 10-volt battery. Oh, it must be an ever-ready. I'm just joking here. You know, battery lasting 5 years, bit of a joke, but you know. Still 10 volts on my battery. Close the switch. Wait 5 years. Do you think the battery's fully charged? So this has got its maximum amount of charge on it. So I'm going to actually even add another, maximum amount of charge. And do you think there's any current flowing? Where's it going to flow to? So if there's no current flowing, then no volts across my resistor, because V equals IR, and there's no potential difference. And there's no current, so I is 0. Yeah? And that means 10 volts is across my capacitor. And, well, my charge is equal to, delta V times C. Maximum charge. They're the two extremes. So I'd like you to be able to tell me what's the potential difference across the capacitor as soon as I close that switch? What's the potential difference across the resistor as soon as I close that switch? I'd like you to tell me what's the potential difference across the capacitor after a long time, and I'll be clear. What's the potential difference across the resistor after a long time? What's the charge on the capacitor at either extreme? What's the current at either extreme? So I'd like you to be able to do those for the extremes.
So we should assume that the capacitor never discharges. We should assume that the capacitor doesn't discharge like after a long time, right?
Yes, I said 5 years to be flippant.
Are you ever going to ask us, like, let's say you have a certain current going through resistor, and you have a certain voltage source, like how much voltage do you have going across the capacitor? Like, let's say you give us a voltage, and then you have a current going through resistor, and then you want to find out.
Oh, that's simple circuits. Yeah, because V equals IR, so you know the potential difference.
Yeah, but like for that formula.
But which formula?
You could be like, what's the voltage drop across the capacitor, and you give us the IR.
Yeah, and that's simple circuits. That's not involving the transient. Yeah.
Does it matter what side the resistor is on if it's only to limit the volt or the charge going to?
It's a series combination. You can swap things around in a series combination.
In real life, but if it takes a certain amount of time to charge it, I know.
No, it's like it doesn't matter where it is in the circuit. Same time. Okay. Because remember that electrons flowing one way is like positives flowing the other way. So it's if I put my brakes on, all the wheel stops rolling. So it doesn't matter where I'm gripping it. Okay, so let's look a bit more mathematically. So we say, well, my EMF and then my potential difference across my capacitor using Kirchhoff's laws, and my potential difference across the resistor, use Kirchhoff's laws equals this, and so I'm just justifying what I said before. And here's a summation where I can say at any instant in time, at the extreme, I'll have no charge across my capacitor, so all the EMF is across my resistor at times t equals 0. And at the other extreme, man, I've got to move this thing around all the time. At the other extreme, there's no potential difference across the resistor because it's all across the capacitor. So there we are. I'm sorry?
T equals a long time. That's very scientific.
Is there a function for in the middle?
Yes. Funny you should mention that because there is. And so I'm going to switch slides because this is actually, well, okay. I'm going to switch slides. So this is for charging. And what happens is we take these laws, and we notice that we have a function of Q and dq by dt, and that's the differential equation. So we need to solve it. Well, we don't, because you don't need to know differential equations for this course, so we pull the solution out of a hat. And we say, well, look, so let's go through it. My maximum charge would be, well, we know that charge is equal to my delta V times C, and I'm calling my potential difference, well, at the maximum, my potential difference is the same as my EMF. So there's my maximum charge. My maximum charge is, this is for little c means charging. This is the Q for charging. My maximum charge would be simply E times the epsilon times C, my EMF times my capacitance. Yeah, eventually it gets there, but it's modified. And it's modified by this differential stuff. And there's my differential stuff. And the solution is it's 1 minus e to the minus t over RC. There's the answer. And I'm not going to justify it and just learn it. T is the time, R is the resistance, and C is the capacitance. And RC is a very useful thing. It's called the time constant. It's a marker. It's like a navigation light. And when T is equal to RC, this is e to the minus 1. Agreed? When T is numerically equal to RC, then this function becomes e to the minus 1. And if you get your calculators and you find your e to the x and you plug in minus 1, what do you get? Do it. Or tell me because you know it from math. It's going to be 0.36, 0.37, 37%. Okay, so at the time constant, you've fallen down, because it's a negative, by 37%. Because this is climbing, we have this awkward mathematical expression, which is it's 1, it's what you're going to get minus this thing. So it basically goes boom, 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 like that. Your job is to know that expression, know it, and to know that the time constant is RC. So when I talk about long times and intermediate times, if I look at a circuit which has a resistance of 10 ohms and a capacitance of 7 farads, what's the time constant? So what's the value? 70 watt. We're using SI units. 70 seconds. So that equals 70 seconds. So at 70 seconds, you have risen to about 63% of your maximum value. So if I was at 700 seconds, I'm way beyond. I'm near my maximum value. You could argue, say, you never get to your maximum value, but you get close enough, it doesn't matter. Yeah. So that's a way of scaling things. So when you see an RC circuit, you just multiply together the resistance and the capacitance, and it tells you, kind of roughly speaking, how long things are changing for. In the time constant, you got to 63% of your effect. Okay, so it's kind of like in among. So I pick instantaneous, I pick long time, I pick somewhere in this period here. So conceptually, I want you to know what happens as soon as the switch is closed. I want you to know what happens in a long, long time, and I want to know what happens in that intermediate part. Okay, that's for charging. Agreed? Discharging. Well, discharging is basically just in a way, mathematically, it's straightforward. If I'm discharging, I lose charge. So how do I discharge? Here's my power supply, here's my charge, here's my resistor. How do I discharge? I disconnect that and I short out that. So I disconnect, I open that switch, and I short this out. So now the currents can flow around that bit. That's how I discharge. And it takes time for that to happen because the resistor is making it sluggish. So the equation for that, now this is QD, Q discharge, so we don't get confused, is equal to, again, your maximum value, but that's moderated by e to the minus t over RC. So you learn one of them, and you remember that the other one has a 1 minus. They're not two completely independent equations. Okay? So your job, know what happens instantaneously, knows what happens after a long, long time, know those two equations so you can say what happens in the meantime, and know your time constant. The time constant is incredibly useful. Yes?
This is kind of tangential, but in the differential equation up there is that epsilon, that's a constant.
Epsilon is the EMF, which is a constant. Okay. Cool. How many people have done differential equations? Yeah. Do you realize, I hope you guys realize that you're pretty much ahead of the game. If you were a typical student at USF, you would not have done differential equations by the time you are ending your sophomore year, entering your junior year. Most of them don't. Physics at USF does not require differential equations. So it's just choices. People say, is it worth it? Is it not worth it? So again, this leads back to the fact I don't want you to ever feel that I'll talk about math. I don't want you to ever feel that your mathematical training, if you've gone through the system here, is anyway light or inferior. The only difference that you've not got is you've not been in a hall with 100 people figuring out what to do. You've been hopefully in a classroom with 30 people with a teacher that takes more time and typically has more experience. Typically. So don't want you to go feeling, man, am I prepared? Chances are you're prepared. You're just not used to working by yourself, getting it from the book, which is more what people have to do in the big lecture hall. It's amazing. How many people here have been in a big lecture hall? So does it feel different? It feels different, doesn't it? One of the research shows that one of the big indicators of student success in a big lecture hall is joining a study group. It helps. It's like 5 pairs of eyes are better than one. How many people here, as a practice, sit at the back? Research shows sitting at the back, you can scale grades almost by how close people sit. There's always exceptions, but by and large, the first 5 rows really engaged. You're making eye contact with them. When they look frowny, you slow down. When they smile and nod, you keep going. People at the back could be, passing out from a total lack of understanding, and you wouldn't even notice. So if you want to affect your teachers, 2 things. Sit at the front and go to office hours. When you go to office hours, you set expectations. Some people write their tests even before the semester. But, you know, if you're asking questions during office hours that the teacher's surprised about, they will slow down. You know? So, and conversely, if you're asking really good questions, they will tend to speed up. And I can't tell you how many times my office hours are dominated by people who I know are going to pass. They're already getting A's. Because it's easy to go to office hours when you're doing well. But, you know, ideally, if people who were struggling came to office hours, then you'd realize as a teacher, oh, they're not getting this. So be involved in your class. I'm going to end it there, and we'll say stop.